All right, before we begin, I'd like to take a quick poll to see who was here at the last week's meeting. It wasn't required, just want to see where everyone's at. So can I get a raise of hand if you were here at last week's meeting? All right, so about 50%. All right, so can I get just a double check? Can I raise of hand if this is your first meeting about neural networks with DSC? Perfect. All right, I'll spend a little bit more time when we go over review then. All right, cool. So today we'll be going over again a review of neural networks. Then we'll start to look at a deep neural network notebook. This is where you get to play around with some code. We're going to talk about the data processing that goes into it, and then further on into deep neural networks and how to build a neural network that effectively predicts or classifies what you need to do. So neural networks. This is kind of a bit what neural networks look like. They're essentially a bunch of nodes, built-in layers that are interconnected with the neighboring layers. As we see here, we have an input layer, which is on the left side. So for instance, this layer, the input layer is consistent of multiple nodes, also known as neurons. Each of these input nodes are representative of a specific attribute in a data set. So for instance, if you are predicting the likelihood of someone to get a heart attack, maybe the first node might be their weight, or the second node could be their height, blood type, and so on. So each one of the input layers is an identifier of some sort of attribute of the data set. So think of it as that input data. The output layer is kind of the prediction or the end goal of the neural network. So for instance, the final layer, if we're doing how likely they are to get a heart attack, could be an age at which we predict them to get a heart attack. If, for instance, we are predicting whether a picture is of a cat, dog, bird, each node in the output layer might represent a probability of whether or not that picture is of a dog, bird, cat, etc. In between these input and output layers are hidden layers. These hidden layers are simply there to help calculate the end result. So we'll talk about how these are calculated, but one of the main things we need to know is kind of how we describe a neural network. So a neural network kind of has two things that we like to talk about: depth and width. Depth is seen as the number of layers in the neural network. For instance, in this neural network, we have a depth of 5 because we have an input layer, 3 hidden layers, and an output layer. So depth of 5. Additionally, we can look at width. Width is the number of neurons in a single layer. So in this case, the width would be 5 in every single layer except for the output layer. We'll talk a bit about how we can use these a little bit later. So how is a neuron calculated? A neuron is calculated using all of the previous layers' neurons. So for instance, if we look at this neuron right here, it is calculated using some formula that uses every single one of the nodes before. Notice how every single node is connected to every node in the next layer. So the main piece, every node is interconnected with the previous and past, or previous and future nodes. So here's a little bit about the math. I'm not going to go too deep into it. Hopefully that doesn't happen again. This is a little bit of math behind how each node is calculated. I'm not going to go into too deep as to how this all works, but again, the key part being it takes in some inputs from the past network, which as we can see here in the input section. It multiplies it by some arbitrary weights. We'll talk about this later, but this is essentially how a neural network learns. They adds it all together with a bias, which again is one of those arbitrary values that will get learned. You don't have to memorize this, but then it puts it through an activation function. Again, we'll learn about this later. And it gets sent as an output or the end result of that neuron. So again, going back, every neuron is calculated using all the values from the previous layer, multiplied by some arbitrary weights, added together with some bias, thrown through an activation function, and we get our output. Again, you don't need to memorize it, just get the general idea. Any questions so far? I'll keep pausing a bunch because this is a lot of information to take in. Cool. So activation functions. These can be a lot of things. So as you can see here, these are essentially non-linear functions that can be used to change up the layer. So for instance, we have the sigmoid activation function, which has a range of 0 to 1. It essentially looks like that, and same with all the rest. The reason we need these activation functions is because when we take a bunch of linear functions, so for instance, f and g of x, they're both examples of linear functions. Very simple. You have a coefficient and a, I don't know, bias value. And so if we take the composite of the two, or we do f of g of x, when we simplify it out, we can still simplify it back to another linear function. Because of that, if we take two linear functions, take them, put one side the other, we get another linear function, that kind of defeats the purpose of having multiple layers. So to rectify this, we use nonlinear activation functions to make it so that this doesn't happen, so we don't accidentally simplify into a single layer. Again, you don't fully need to understand this, but we'll talk about activation layers later, how to choose which function to use, and so on. So as I talked about before, exists these concepts of weights and biases. These are arbitrary values that will get trained and slowly learned through backpropagation. Again, I'll talk about what that means in a second. So these are just values that will get automatically identified by the function itself, or by the neural network as it trains. So how do we actually learn? So the goal of almost all AI models is to have some sort of loss function, or a way of calculating loss or how well it's doing. In this case, we are calculating it by the probability it gets something incorrect. So as we see here, there are trying to predict 10 things, or it predicts 10 times whether someone is making less than or greater than $50,000. In this case, if we look at the orange arrows, we could see it mispredicted 3 times. Because of that, we would get our loss to be 0.3 or 30%. The goal, obviously, would be to get this to become 0, because you would want it to be perfect or have 0 loss. So again, the goal of the neural network is to optimize for the minimal, or trying to get as close to 0 loss as possible. So how do we calculate that? There's a bunch of different formulas. Again, we'll go over this later. But the main idea, again, to remember is we're trying to minimize this loss. And so we're trying to figure out what are the best weights and biases to help minimize that loss when we go predict and everything. Cool. And then how do we actually calculate that? Or how do we identify how to change these weights and biases? We do this through backpropagation or gradient descent. Kind of think of this as finding the slope of a graph. So if we look at here, we have a graph of loss as put over the value of weight. And so we're trying to identify how should we modify the weight value, or this dot here, to minimize loss. Can anyone here tell me how we'd want to change weight to minimize loss in this based on this graph? Don't forget, we're looking at the slope here. So how would we want to move the weight here to make it so that we have a lower loss? Yes. Exactly, we want to move it to the left to help minimize the loss. So as we can see here, we kind of take the slope, we have that arrow that points to the left, and so that kind of tells us, hey, we want to move the weight to the left, or decrease our weight to hopefully minimize the loss function. We do that, and then we can keep going this again. Can then someone tell me how we want to change the weight again to minimize loss? Very similar to what I just asked. Yes. Exactly, we move it left again. We want to keep going the same direction as our slope, or the derivative of this. And so we keep going to the left until eventually we find, hopefully, a absolute minima. Can someone tell me a potential problem with this? What's the case that it might not do exactly what we want in terms of optimizing loss? Back there. Exactly. You can accidentally find a relative minimum. So that's one of the key problems with these neural networks, is that when it tries to optimize and minimize that loss, it might get into a valley that isn't necessarily the absolute minimum. Another thing I'd like to go over, some just a basic vocab, is epochs, basically the number of training iterations. So every time we kind of said, hey, let's change our weight value, that is equivalent to 1 epoch. So we can say, I want to train using 30 epochs. It'll train and modify the weight values 30 times over. The learning rate, it essentially says how much do we actually want to change at each iteration. So for instance, a bigger value means kind of bigger jumps in the weight changes. lower values represent lower jumps. Sometimes maybe we'd want a higher learning rate to kind of jump over those values that we don't want. Sometimes we want lower, just depends on the problem and also depends on the optimizer that we'll go into later. Here's a quick GIF as to what this looks like. Again, this is all a quick overview. You don't have to fully understand everything. I'll go over in a bit what you should be taking away from this. So things to take away. So essentially, I would like everyone to know that neural networks are very simple. Did everyone hear me? You get thumbs up if you can hear me. Perfect. Okay, we'll use this one. So some things to take away from what I just talked about. So the main thing with neural networks is there's a bunch of different layers of interconnected nodes or neurons. You don't necessarily need to know how they're interconnected. If you do, that's a bonus. Another thing, like you kind of remember from that is that every single node value is calculated using a combination of all of the previous layers nodes and some of arbitrary weights or bias values that will be trained. And the way we train is through a form of gradient descent, also known as backpropagation, to hopefully minimize loss. So again, the goal is to minimize loss and to be able to train these weights and biases to hopefully predict accurately. Cool. So let's go over the Collab Notebook. So if everyone can go, you're up. All right, could I get a raise of hand if you're able to get to this line? Cool. And you'll have to use a laptop. It's kind of hard to do this on a phone. So if you have your laptop, please take it out. All right, so once you go to the notebook, you only have view access, so you'll have to create a copy of it. So once this loads, you want to go to File, save a copy and Drive. You should get your own copy that you're able to edit and save. For those from the previous meeting, this is a completely new notebook. We'll talk about the differences in a bit. Another thing I would like everyone to change is go to Runtime and click Change Runtime. By default, it is set to CPU. In our case, we want to run on a T4 GPU. This essentially enables us to run all our calculations significantly faster as GPUs allow us to utilize parallelization. Basically, GPUs are faster than CPUs when it comes to training neural networks. Cool. Does anyone have any questions? Yes. Yes. Oh, wait, let me adjust it on the other. Here. Good. Any other questions about anything that we've covered so far? Cool. Can I get a thumbs up if you're feeling good, thumbs middle if you're kind of and thumbs down if you're a bit lost? It's best if I get everyone's feelings just so I know if I should go over things again. Okay, so mostly thumbs up, some thumbs in the middle. Perfect. All right, cool. So every time we train a model, it will take some time. So sometimes I'll ask you to run things and then we'll go back to it in a bit. So right now, we'll run the entire notebook and we'll see the results as we walk through it together. So to run everything, click Runtime, go to Run All. Can everyone see the screen perfectly or should I zoom in? Anyone need me to zoom in? All right, perfect. We'll keep going from here. So the first thing we want to do is we want to import all the necessary libraries. I'm not going to go too much into depth about the libraries, but the main idea is one of the best ways that we're using this is through TensorFlow and Keras. Those are the Google developed libraries that help us build these neural networks in much easier ways of having to code it from scratch. The next step is about actually downloading the data. So right now I have a large CSV just downloaded onto my GitHub page. And we're just cloning that to be able to use that for our notebook. If you'd like to see the data set we're using, we are using a cover type prediction data set. Essentially, we're given a bunch of these attributes. as you can see here, you can read those on your own, to help identify what type of cover or the land type is that area. So for instance, it could be spruce or fir, lodgepole pine, aspen, Douglas fir, etc. We're able to use the attributes such as elevation, aspect, slope, etc. to help identify these things. The goal is to create a neural network that uses all those attributes as inputs to be able to identify or classify which of the 7 classes that piece of land is. So if we see here, this is another way of showing the data. If you want, you can look through this, a bunch of different types of attributes that we're using here. So the next step is actually cleaning up the data. So we clean up the data in 2 main ways. So we use undersampling and data normalization in this case. There's a lot more ways that you can actually go into manipulating the data, but in our case, we'll be just using those 2, and then we'll split up the data into train and testing splits, which I'll talk about soon. All right, so the main thing that we're using is called undersampling. Undersampling is used when you have a non-equal amount of data for different classes. So for instance, if we look at the graphs here, for the dogs, cats, hamsters, and birds, most of all dogs, cats, and birds, we have a lot of data for. We have around 90 pieces of data for all those 3. But for some reason, hamsters, we weren't able to collect maybe enough pictures for that. So maybe we only had 30. We can use undersampling and say, hey, I would only like to look at 30 dogs, cats, birds, and hamsters. And therefore, there's about an equal amount of data of each type or each class to be used in training. So we do something similar here. I don't know if I've shown this, but there's significantly more of certain types than others in the data set. So we want to do the undersampling, where the number of samples is 6,000. So that's the first step of data cleaning that we do. Again, you don't have to memorize all this. These are just things cool to know, so that if you go build your own, you'll have an idea as what tactics I might do in certain situations. Another thing that we're going to be doing is data normalization. Data normalization helps to change the data to help represent it in more either accurate or helpful ways with training. So for instance, I don't know if you guys can really see the numbers, but on the left on this graph here, we have the raw data value. So it's values between 5,000 and 45,000. And there's a bunch of different normalization techniques. The ones we're using here is called scaling to a range. Essentially, we're changing all of the output values, or all the values, from 5,000 to 45,000 into just 0 to 1. This helps in training the neural network, as it doesn't have to deal with such large values, so it's a little bit easier to deal with when we actually start to do all the calculations. There's other ways such as flipping, log scaling, z-score. Again, I'm not going to go into depth about these, but main idea here, takeaway, is data normalization helps to change the numbers to help represent them better for calculation later on. Another important step is splitting up our data into training data and testing data. So for instance, when we have to train our neural networks, so when we're changing the values of the weights and biases, we don't want to be testing to see how our network actually does using the same data we train, as that can create some biases or can accidentally overtrain certain data. So we want to split it up, as we can see that we do here in the code. So we take in all of our data, we split it into our training test sets. The X, again, would be the input, Y would be the classification, or the true classification. Any questions so far on the cleaning up the data? Again, you don't have to memorize exactly how everything works, just get the general idea as to why we might be wanting to do this and kind of the names. Cool, how are we feeling? Can I get thumbs up, thumbs middle, thumbs down as to how we are feeling about this so far? Just want to see what kind of pace. All right, so thumbs up and some thumbs in the middle. Cool, we'll keep going. All right, so for those that were at the last meeting, you will recognize kind of a model that looks like this. This is how we build a neural network using TensorFlow. We start off with a sequential model, meaning that we have these layers in sequential order. Again, that's identical to what we showed earlier with the models. It's just layers one after the other. Let's see if I can go back to that slide. Yeah, as we see here, it's just sequential layers one after the other. There's a bunch of different things, such as recurrent neural networks that I will not be covering that you might want to use something different. But in this case, we're talking about sequential, the most basic layers here. Additionally, you'll see I add a norm layer. This was just used for the normalization. You don't have to worry about that right now. It's just something that we use for the data cleaning that we talked about earlier. The next lines, you see I add dense layers. These dense layers are just regular layers that we talked about earlier, that concept of a linear layer. That's what a dense layer is for that. And the first number you see, that is the number of neurons within that layer. So for instance, as you see here, the first layer is of size 10, meaning the hidden layer there is of size 10. So it would be 10 neurons within that first layer. In this case, we have an input shape. Because it is the first layer in the network, we need to say how large our input size is. So in this case, we have 54 attributes, so 54 things that describe that land cover area, and that is used as our input layer here. That's nice. Again, ours is a size of 54 because we have 54 attributes that we're giving it. The activation function, talked about a little bit about this earlier, but this is just used for non-linearity purposes. We'll talk about how we can choose the right function. Just there's a bunch of different ones, such as ReLU, sigmoid, tanh, and a bunch of others. Once we add all those layers together, our final layer has to be the number of things that we're trying to classify for. In this case, there are 7 land cover types, so our output layer would need to be of size 7. Does anyone have any questions about how we build our neural network here? We got thumbs up, thumbs middle, thumbs down about this so far. Building the neural networks. So people that were here last week, you probably recognize this bit. People are new, this might be a little new, but it's a pretty easy change. Plus, I've added a bunch of documentation if you'd like to check it out later. Cool. Let's move on. So next part is to find a bunch of different things that we need to know. For instance, the optimizer. So there's different optimizers that exist. This is how we actually calculate how to change the training values. In this case, SGD, also known as stochastic gradient descent, is how we're calculating this. Again, I'll talk about what this means, how we can change this later on. The loss function we're using currently is mean squared error loss. Again, I'll talk about this later. Epochs we talked about. And then once we have all that set up, we want to compile it all together. Say, hey, TensorFlow, this is what we're actually doing. I'd like you to save all these values. Then when we actually want to train our neural network, and when I say train, that means when we want to actually modify those weights and biases to get a neural network that predicts what we actually want to. So in this case, this is where we actually train data. So as you can see, it has slowly trained over the different epochs. In this case, it's out of 30 epochs. So at the very first iteration, we see it was not doing very well with 0.23 accuracy. Can everyone see that? Or do I need to zoom in? I think I'll zoom in a bit. Cool. So as we see on the first epoch, it didn't do very well because it did not train these values yet. Right now, they're just initialized to some random variable that might not be that helpful for us. So again, we start off as really poor accuracy, but over time, you can see that our accuracy slowly increases until at the very end, we get an accuracy of around 0.68, some value. In this case, our accuracy of predicting those 7 things is 68%. If you want to see, we're able to graph it in the next one. This just shows the loss over time, or the loss over the epochs, and the accuracy of each of these epochs. The goal for this is to be able to get, again, as high accuracy as we can, or to minimize the loss value. But as we see here, our accuracy has started to taper off. So if we see that, it probably means that we don't need to increase the number of epochs, as it will continue to go with this trend and won't train as fast. But when we started, it was training a lot faster. Again, don't worry about all this. We'll cover a bunch of this later on. Additionally, when we split up our training and test set, we can see the test accuracy. So this is now using our trained network. How does it deal with a different data set that wasn't what we used to train it? Now we have some more ways of visualizing data here. Again, this is a graph with our predictions if you scroll to the right, and a confusion matrix, which tells us what it guessed for each of these responses. So for instance, the y-axis is the true values. So the rows are the true cover types, and the columns are the model predictions. Okay, any questions about what the notebook is? Again, we'll go through this some more later on, so if you're still a bit iffy, don't worry about it. But any questions that you guys have? Cool. Let's go back to the slides. Actually, first, before we actually continue on, I'm going to split you guys up into groups. So if you can go
group up with around 4 people that are around you. And for the next 5 minutes, I'll let you guys play around with changing these different variables to see who can get the most accurate neural network as of the next 5 minutes or so. So again, talk to the people next to you. If you don't have anyone, raise your hand. I can come around and split you guys into groups. So 5 minutes, try to see what kind of accuracy we can get for our neural networks for this specific data set. All right, everyone, we'll come back together. Can I get some thumbs up as to how we're feeling? Thumbs up if you're feeling good. Thumbs middle if it's eh. Thumbs down if you're kind of lost. Again, if you're not feeling the best, it's okay. Hopefully, when we keep going, everyone will get a better idea as to how everything works. Cool. All right, what kind of accuracies does anyone get? Did anyone get accuracies between 60 and 70% accuracy? I got to raise a hand if you got between 60 and 70. All right, a little bit. Anyone get between 70 and 75? Raise your hand, 70, 75. Okay. Almost everyone got 70, 75. What about 75 to 80% accuracy? Okay, did anyone get above 80% accurate? Ooh, what was, okay. What can you do? Anyone higher than 81% accurate on the test data set? Was yours on the test data set? Or is it on the train that got over 81%? All right, what did you guys get over here? What accuracy did you guys get in the testing? 84.1. Wow, that's impressive. What about the someone raised their hand in the back? What accuracy did you get on the test data set? 82.3. Okay. So hopefully by the end of this, everyone will hopefully get accuracies of around 80 something percent. That's kind of our goal. So we'll talk about how we actually want to change these values to hopefully optimize and get the best accuracy of the lowest loss. So let's go back to the slide. So let me skip forward. So what is a deep neural network? Last time we talked about regular neural networks, but today deep neural networks just mean a neural network that is multiple layers deep. So essentially all the neural networks we were talking about last week is still considered a deep neural network because it's just a generic term for neural networks. Typically you consider bigger networks deeper. Again, we'll talk about that a little bit later. So we showed a little bit about how we build the neural networks through the code, but now how can we actually make this model a little bit better? So one of the big issues that people tend to find when they're training networks is the concept of overfitting. Overfitting tends to happen when the model ends up learning the noise rather than the actual data or patterns within the training data set. So essentially, it's memorizing the training data. And this typically can be seen when the training accuracy is significantly higher than the testing accuracy. And that's something we typically want to avoid. I don't know if many of you guys saw that problem when you guys were messing with the neural networks where the training data was significantly more accurate than the testing data, but that's something that you will often see when building really large neural networks. And so common ways to avoid this issue is one, just have more training data, which if we're being honest, is probably the hardest thing to do out of all of this because collecting data is not easy. Another thing we could do is to reduce the complexity of the model. So as many of you guys tried, you probably tried adding more neurons or more layers to your neural network, and that will add complexity, which will typically cause more overfitting or even sometimes a worse neural network overall. So for instance, we can fix this by decreasing the number of hidden layers, reducing the number of nodes, basically decreasing both the width and the depth of these neural networks. Additionally, we can also decrease the amount of epochs or the iterations that it will take to train the model. Again, you can play around with this a bit later. And another big thing is the concept of dropout, which we'll get into now. So dropout is an interesting idea, which essentially zeroes out random neurons. So for instance, when you're training a model, it will be very simple and where every node is connected to the next node. Dropout essentially deletes random nodes from the neural network. And the reason we might want to do this is to prevent the concept of co-adaptation, or when multiple nodes in the same layer learn the same thing. So for instance, let's say a single node might be identifying a vertical line in a picture. And let's say for some reason, your neural network has two of the nodes that learn the exact same thing. That might cause an issue in the later layers because two things have learned the identical things. You can use dropout to help fix this issue, which will zero out random neurons. We can actually control the amount of neurons that get zeroed out, and this is called a dropout rate. So for instance, if we set the dropout rate to 1/2, that means we want all the layers, or we want half of the neurons in the previous layer to be zeroed out at random. Typically, this value is around 0.1 to 0.2, but you can play around with what happens if you use higher or lower dropout values. Sometimes it's helpful, sometimes it's not. Dropout is one of the biggest things when used in overfitting. So that's when the model does a lot better on training data than it does on testing data. So the way we add dropout is very similar to the way that we add another layer. You guys probably can't see this. It's okay. I'll code this up a little bit later. But you basically do model.add, dropout, and then a dropout rate. Again, I'll type this up in a second. Another thing that we can play around is with the depth of our neural network. So these are kind of nice rules of thumbs that we can follow when actually building our neural networks and identifying how many layers that we want. So if our data is very, very simple, so it's linearly separable. So think of how your BMI, I think it's just the product of your height and weight. Can be wrong about that. But for instance, if we're predicting BMI, we could just do 0 hidden layers, as that kind of data is linearly separable. However, if you have more complex things, you might want to use a little bit more hidden layers. So if you have less complex data, you might want to use 1 to 2 hidden layers. If you have like really large amount of attributes or things that you're trying to classify, you might want to use a little bit more like 3 to 5 hidden layers. But anything really above that will typically tend to lead to overfitting. Plus, just having more layers will take longer to train. So not always is extra layers always going to represent a better neural network. So sometimes it is better to actually reduce them. We'll see that in a second. So again, here's another example as to what we may be talking about, where if you use 0 hidden layers, that can represent any linearly separable function. 1 hidden layer, there's a theory that exists out there that says one hidden layer with some finite amount of width can predict everything. Again, that's all theoretical. In practice, you probably don't want to be doing everything 1 hidden layer. 2 hidden layers, is a lot better for almost everything. It can still predict almost anything to almost any level of accuracy, just depending on the width that you put these layers at. Again, play around with what happens when you use 1, 2, 3, or even more hidden layers. We'll go with the layer about how we can actually code this. All right, so now we'll talk about the width. Another thing we can do is we can change the number of neurons within a single layer. There's a couple of rules of thumbs I've written here. There are some math equations, but they all basically come down to the point of you don't want to have way too many you don't want to have way too many neurons. And you also don't want to have a very little amount of neurons. So typically, I'd say think about the number of neurons you want is somewhere in between the number of attributes and the number of labels that you're trying to classify. So in our case, we're using an input size of 54 and output size of 7. So maybe our width should be somewhere in between. Again, you could play around with this to see what works better. But these are some rules of thumbs that you can kind of follow if you don't know where to start. There's some questions here, but again, the main thing is just probably keep it in between the two or somewhere around the output size or the input size. All right, cool. A quick overview of this. So again, I talked about a lot of it, about the background, but the main things I'd like you guys to take away from those quick slides were 1, dropout is used to reduce co-adaptation by zeroing out random neurons. That should be hopefully pretty simple. You don't need to know the math or exactly why that works, just the idea of what dropout does. We also want to reduce the number of layers and the size of these layers. So we want to keep our layers usually between 1 to 4 layers and our width somewhere in between the input and output size. And a typical rule of thumb you want to follow is you probably want to increase your depth rather than your width when predicting things of more complexity. Again, don't worry about too much about that, but let's go into actually coding. So let's say we have our neural network here. Let's go employ those changes that we just talked about. So for instance, let's say I only want to have 2 hidden layers. Again, you can choose however many you want. So let's see what happens when I go around and start deleting some layers. So because I only want 2 hidden layers, I can go ahead and delete these 2 layers right here. So let's just change this back to 10H just because. And so now we have 2 layers, and we have one of size 10 and one of size 50. Let's change these to be somewhere in between 54 and 7. Let's just try 40. Why? Because it's around somewhere between 2. Again, you guys can change these to be whatever you'd like, but we'll play around with this. And if you want, you can add a dropout layer. If you were to add a dropout layer, it would look something like this. Model.add dropout, and then the size of the rate of the dropouts. In this case, our dropout rate could probably be 0.1. Again, you could play around with these different values, but hopefully this will have a better result. So we can run this, and we'll keep all this same. We'll talk about how we can change this a bit later. So let's run this. Hopefully it trains with better accuracy. So as you can see already from the get-go, we already have significantly better accuracy where our first iteration, it was like 0.16 or 16% accurate. Already you can see by the first iteration, we are at 37% accurate, and we are climbing a lot faster than we had before. So just simply reducing the number of layers, the number of neurons within each layer has shown to significantly help when predicting. Again, we'll keep playing around with this, but this should take a couple minutes to train. And while it's training, does anyone have any questions about reducing the size of neural networks, the concept of overfitting, or anything like that? Any questions? So raise your hand. Cool. How are we feeling about this so far? Get thumbs up, thumbs middle, thumbs down as to how people are feeling about this. I'm seeing a lot of thumbs in the middle. Is there anything that you guys have any questions about that you might be struggling a little bit with? And don't worry, if you probably find something difficult, you're definitely not the only one. I can guarantee you that. But it was a bit complicated again. The main thing I would like everyone to take away from what I just went over was this quick thing again, what the concept of dropout is, the kind of the size of the layers that we should be expecting, and the concept of increasing depth is typically more important than increasing width. I'm not too sure. I don't remember what the original actually before was. It's about the same. So let's run our plotting cells and the actual test accuracy. All right, well, while this is running, we'll continue on with the slides. So another thing that we would like to change a lot of is activation functions. So there's a bunch of activation functions that are really common, including sigmoid, tanh, ReLU, a basic linear layer, which we'll talk about in a second, and softmax. Again, there's a bunch more, but let's go into when we would use one over the other, or why we might want to use some. There's two main uses for activation functions. One is for the hidden layers. So this is used again for the concept of non-linearity, so that when we combine a bunch of layers together, they aren't just equivalent to a single linear layer. And so sigmoid, again, is this function right here. The equation here, you don't need to memorize the equation, but just getting an idea is what this looks like. It's kind of like a logistic regression looking graph. Tanh, I'm sure everyone's at least heard of tanh before, but it essentially looks similar to sigmoid. But the main difference between tanh and sigmoid is the range. So sigmoid, the range is 0 to 1, whereas tanh, the range is -1 to 1. So in this case, you might want to use tanh over sigmoid, depending on what you're predicting here. Another really common one is ReLU, which is very self-explanatory, or very simple when it comes to actually calculating it. It's just the max of 0 or x, which then takes the input, and if it's negative, it sets it to 0. If it's positive, it keeps its value. Pretty straightforward for how ReLU works there. Common output layers are the linear layer. So for instance, if you still do want to output a value between -infinity and +infinity, you might not need to actually change the output of it, because at this point, we don't necessarily care about the concept of non-linearity when it is our final layer, because we're not combining anything. So sometimes you might want to use a linear layer. Sometimes you might want to use a sigmoid layer. So for instance, if you are if you're classifying a probability, which are between 0 and 1, the sigmoid function would be very helpful here, because again, the sigmoid range is between 0 and 1. Additionally, softmax, I'm not going to go too much into softmax, but it's used for multi-class classification. If you would like to identify which activation functions you want to use, you can see this kind of decision tree here. So for instance, if you're using a multi-layer perceptron, also known as a regular neural network, you'd want to use ReLU. We'll go into why in a second. If you're using a convolutional neural network, which we haven't gone over, and probably won't, you'd also want to use ReLU. The current neural nets, sigmoid, tanh, again, not go into those. For the output layer, it depends on what problem you're trying to solve. So again, if you're trying to do binary classification, you'd probably want to use sigmoid activation. If you're doing multi-class classification, softmax, multi-label classification, sigmoid, and if you're doing regression problem, which is basically guessing a number between -infinity and infinity, you'd want a linear activation function as your output. Does anyone have any questions about activation functions? I didn't go into the math of it, but any general questions about that? Cool. So one of the big concepts of activation functions and how we're able to choose which activations to use is the concept of vanishing gradient, which is a huge problem in machine learning. The vanishing gradient problem essentially says that when we calculate the gradient or the derivative of each of the layers, they get exponentially smaller as you go back in the layers. So for instance, if we use the sigmoid activation function at every single layer, when we calculate the first derivative, so the derivative of that first layer, the value will always be between 0 and 0.25. Because if we look at the sigmoid function, the derivative is never greater than 0.25. So because of that, the first layer, the gradient or the derivative will never be greater than 0.25. And if we look at the second layer, it will also not be anything greater than 0.25. And so as we're going back propagation, so going back through the layers, these numbers will keep getting smaller and smaller. So at first it's 0.25, And next time we start off with 0.25 and we multiply it again by the next derivative. So again, it keeps getting exponentially smaller. So 0.25 squared, and then the third layer might become 0.25 cubed, and so on. So we keep getting a smaller and smaller gradient, and therefore it becomes increasingly harder to learn at subsequent layers. So instead of sigmoid, we use the ReLU activation function for the hidden layer. So almost entirely, when you're choosing your activation functions, ReLU is the king. You almost always want to use ReLU because of the concept of vanishing gradient. Again, the concept of vanishing gradient is a bit more is a bit hard to understand, so it's okay if you don't fully understand. The main idea is in your hidden layers, ReLU is your best friend. You want to use the ReLU activation function, which again was that max 0, x. That's if the value is less than 0, set the output to be 0. If it's greater than 0, just keep the output the same as the input. And so the reason we want to use ReLU as it solves the vanishing gradient is because the gradient of ReLU is always going to be 1 or 0, and so we won't have that vanishing gradient. The gradient will not get smaller as we go back through the different layers. Again, you don't fully understand the vanishing gradient problem, just identify that typically you'd want to be using ReLU within your model. So again, you can change that within your code above. You can play with that on your own, but we'll get to that once we get to the next sections. So loss functions. Loss functions are how we calculate how well the model is doing. This is kind of how we're approximating our success. Or in this case, because it's loss, it's calculating our failure. There's a bunch of different equations for that. Common one is called mean squared error, which kind of follows the concept of take the difference between the predicted value and the true value, square it, and do that for every single prediction, and take the average of that. And so we end up with a graph like looks like that top one where it's almost like a parabola. Where the big thing about mean squared error is it means if we ever have outliers, so for instance, situations where our prediction was really far away from our true class, then it will exemplify and really identify and say, hey, we really do not like that. We were really far away. So it's better. It's the mean squared error is typically better for regression, where it has larger penalties for those outliers or situations where we mispredict significantly. Another calculation for error is the mean absolute error, which is very similar to mean squared error, where instead of actually squaring the difference, we take the absolute value of the difference. And these are very similar, but it's more robust to outliers. So for instance, if you have a prediction that is really far away from the true value, it won't treat that as important as maybe the mean squared error. And both of these are very useful for doing regression problems. Again, regression problems are when you're trying to guess a number. So for instance, if you're trying to guess the temperature of something, that is a regression problem. If you're trying to guess the probability of something, that's also could be considered regression. Another type of thing is classification problems. This is when you're trying to identify whether something is of type A, B, or C. So the notebook that we're looking at, so predicting cover types, is a classification problem, in which case we'd want to use a concept called cross entropy or log loss. Again, it's a very complicated loss function. I'm not going to go into it, but binary cross entropy, which is used when predicting between one thing or another, it's very helpful for the classification problems. Or multi-class cross entropy is useful again for when you're trying to predict multiple classes. And so these are 4 main loss functions you might want to look into. Again, mean squared error, good for regression, mean absolute error, binary cross entropy, and multi-class cross entropy. Again, you don't need to know the math too much about it, but these are the different use cases of these loss functions. Optimizer. So as we talked about, the way we optimize or change the different training values, the weights, the biases, is through this calculation of the gradient. And so the most common concept is gradient descent. And this was evolved into the concept of stochastic gradient descent, where stochastic just means it takes random samples when it does perform the derivative or gradient solving problem. The rest of these, I don't expect you guys to memorize. I barely know what half of these are. There's stochastic gradient descent with momentum. So imagine riding down on a skateboard down a hill. If you hit a little bump, you'll still go over the hill or still go over the tiny bump because you keep your momentum going down the hill. So think of that when calculating the minimum. You can add momentum. That's one iteration upon the optimizers. Other ones exist, such as AdaGrad or adaptive gradient descent. This is where it changes the learning rate automatically. So for instance, as you are on your 500th epoch, your learning rate might not be as large as your first epoch. There's root mean squared propagation. That penalizes when you have oscillating derivatives. So for instance, let's say you are on a skateboard, you're going back and forth on a hill, finding the hill, going back and forth. Root mean square propagation, or RMS prop, it's typically better for minimizing how many back and forth times you go to. None of those matter. The main thing that I would like everyone to take away from this slide is the ADAM optimizer, or adaptive moment estimation optimizer. This is essentially all the things I just listed all put in together. So anytime, pretty much almost anytime you're using an optimizer, you will be wanting to use the ADAM optimizer. It is extremely powerful and is able to converge or find that minimum significantly faster than stochastic gradient descent. So for instance, if you're using stochastic gradient descent with a learning rate of 0.1, you might want to change that a lot when switching over to ADAM. So when you're going to ADAM, maybe divide that by 10 or 100. So we can look into that in a second. But again, the main thing to take away from this slide is to use the ADAM optimizer, as it is a combination of all these different iterative improvements that we've seen on the different optimization methods. So you can go change all that. Then we'll show that in the code in a second. But the quick overview of those things I just went over. ReLU, when it comes to hidden layer activation functions, is your best friend, as it solves the gradient, solves the vanishing gradient problem. Mean squared error is good for regression problems, whereas cross entropy is used for classification on the output activation function. And the ADAM optimizer is essentially the best optimizer that you can use. There's other ones like NADAM, not going to go into those, but those are the main things I'd like you guys to look into. So let's go ahead and actually go and code those things. So the first step we want to do is we've learned that, hey, ReLU is the best activation function for almost all situations in this case. So we'd like to change from TANH to ReLU. We want to change our final activation function because we are doing multi-class classification. We want to be using the softmax activation function. Again, not going to go too much into depth about what that is. From here, we can go ahead and change our loss function and our optimizer. So for our optimizer, again, we'd like to use ADAM. So we can just type ADAM there, and let's set our learning rate to be significantly lower, so 0.01. Again, you can see what happens if you change that value. Because our learning rate is significantly smaller, if you want, we could change the epochs. I'm just going to increase the number of epochs. Again, you guys can play with this however you like. For the loss function, we're going to be using categorical cross entropy as it's defined in TensorFlow. If you'd like to look up all the different loss functions, again, all the documentation is linked above. So let's put categorical cross entropy. So the other option for cross entropy is binary. But because we are predicting multiple things, we don't want to be using binary cross entropy. All right, cool. And let's let that train. Oh, I broke something. No, I misspelled it. Ah, perfect. Cool. Well, this trains. Does anyone have any questions about what I talked about so far? How are we feeling about this? Can I get thumbs up, thumbs middle, thumbs down? Again, you don't need to know the math or really the reason behind it. Just the main idea is how to choose different activation functions or the loss functions depending on the situation given. Can I get thumbs up if you're feeling good? Thumbs middle if it's thumbs down if you're a bit lost. Okay, if you're a bit lost, lot to go over in about an hour. Cool. So while this trains, you guys can go talk amongst yourselves about continuing on here. You can see, I know it is 6:30, so if you have to go, you can go. I don't know if we have what feedback. Oh, we have a feedback form, I guess. I forgot about that. Yeah. You can please fill out the feedback form. Unfortunately, we do not have a price for this, but it really does help us a lot for identifying what workshops you guys would like to see next, how we did, how we can better prepare these for the future. So please fill out the feedback form. It helps us. It makes these meetings better for you guys. In the meantime, if you'd like, you can continue playing around with the notebook and see what kind of accuracies that you guys can get. I'll be here for the next 15, 30 or so minutes, however you guys like. Again, if you have any questions, raise your hand or come up to me. I'll be here for a bit. And thank you guys for coming. Again, please fill out the feedback form. It helps us a lot. Yeah. Here.